When we look at concrete, we see something permanent, right? Solid, unchanging. It's the very foundation of our world. But what if I told you that on a long enough timeline, all that concrete is actually moving?
So let's really get into that. Is the foundation under your house or the bridge you drive over every day actually static? Turns out the answer is a definite no. It has a secret life, this incredible slow motion dance that engineers have to understand perfectly.
And this is just a perfect way to picture it. Imagine a bookshelf. It doesn't sag the second you put books on it, right? It takes years of that constant, steady weight. Well, concrete, under the massive load of a building, does the exact same thing. It's a gradual, almost invisible change over time. Now, this whole phenomenon, this slow movement, it has a name. And for engineers, trust me, it's a huge deal. It's called creep. Okay, so here's the most important part to get. Creep is not the initial bend or compression when you first apply a load. Nope, it's the extra permanent deformation that happens because that load just stays there for a really, really long time. And this chart lays out the difference perfectly. On the left, you've got your instant elastic strain. Think of it like pressing on a spring. It squishes. But if you take the pressure off, it bounces right back. It's recoverable. But on the right, that's creep strain. That's the slow burn, the long-term change. And the big difference? It doesn't bounce back. It's pretty much permanent.
All right, so we've defined it. But this isn't just some abstract concept from a textbook. This slow movement has very real and, honestly, sometimes very surprising consequences for the world we live in. Let's start with the bad side of creep, because if you don't account for it, it can cause some real headaches. We're talking about beams and floors sagging way more than you'd expect over their lifetime. It can make columns more likely to buckle. And in really advanced stuff like pre-stressed concrete, creep can actually cause it to lose some of that critical tension that makes it so strong. But here's where the story gets really, really cool. Creep isn't always the villain. Inside a reinforced concrete column, it actually leads to this amazing, kind of clever partnership. So picture this. When you first load up a column, the concrete and the steel rebar inside it are sharing that load. They're a team. But as the years go by, the concrete starts to creep, and it can't hold its share of the stress quite as well. So what does it do? It's like a tired teammate shifting the weight. It gradually transfers more and more of its load onto the much stronger steel rebar. The steel just picks up the slack. How amazing is that? So yeah, creep isn't just a problem to manage. In some situations, it's actually a feature, not a bug. Sometimes it's the hero of the whole story.
And this is called stress relaxation. Imagine a piece of concrete that's locked in place. It can't expand or shrink freely. As temperatures change, huge stresses can build up inside, stresses that could literally crack it apart. But creep lets the concrete deform just a tiny, tiny amount. It's like a safety valve that lets the pressure bleed off, which can actually prevent those cracks from ever forming. Okay, so we've seen what creep does, the good, the bad, and the surprising. But what is actually happening deep inside the concrete to make this happen? Let's get into the science. Well, you can think of creep happening in 3 stages. First, there's the primary stage, where it happens pretty fast, but then slows right down. Then comes the long haul, the secondary stage. This is a super slow, steady creep that can last for decades. It's where most of our structures live out their lives. And then there's a tertiary stage, but you'd only see that if a structure was under extreme stress and about to fail. It's not something we expect to see. And get this, scientists still don't have the exact mechanism totally figured out. Isn't that wild? The leading theory is that it's all about water molecules trapped in the microscopic structure of the cement. Over decades, that constant pressure slowly squeezes the water out, almost like wringing out a sponge in super slow motion. That tiny movement on a massive scale is what we see as creep. So this raises a really important question. If concrete is always moving, how on earth do we build anything that's supposed to last for centuries? Well, this is where the genius of engineering comes in. And here's probably the biggest takeaway of all. Engineers don't try to stop creep. You can't. Instead, they embrace it. They know it's going to happen, they calculate exactly how much is going to happen, and they design the whole structure with that movement in mind. It's just part of concrete's DNA. And they have this whole list of ingredients to help them predict it. Things like the humidity in the air, wetter air actually means less creep. The age of the concrete when it's first loaded is huge. Older concrete is stronger and creeps less. Even the type of rock used as the aggregate makes a difference. All these details matter.
So how does this all come together in the real world? Well, modern building codes basically give engineers special formulas. These formulas let them adjust the stiffness of the concrete in their computer models, telling it, hey, this material is going to get a little bit softer over the next 50 years, so make sure you account for that. It's all about designing for the long haul, not just for day one. Let's pull it all together now. What this really means is we have to change how we see the world around us. Our buildings, our bridges, our dams, they aren't just lifeless objects. They're dynamic systems, slowly and constantly responding to gravity and time.
And I think this quote just nails it. The best engineering doesn't try to force a material to be something it's not. It's about deeply understanding its nature, like creep, and then using that knowledge to work with it, to create something incredible that will last. So when it's all said and done, this secret life, this slow-motion movement of concrete, isn't something to be afraid of. It's a completely understood, totally predictable, and carefully managed force that is factored into the design of every major structure you see. It's all part of the plan.
Which kind of leaves you with one last thought, doesn't it? We've just pulled back the curtain on this one amazing invisible force. What else is out there? What other secret behaviors of materials are quietly shaping our world right under our noses every single day?